Okay, this is 7.3.2. Rather than a common external tangent line, we also have a common internal tangent line. And in this case, it is the line CB, which is between these two circles. And you can see that what I've done is kind of create a common internal tangent, right? And it's really movable. But what's very cool is that we have this line, CB, touches the circles only once, and but it's common to both. And again, we have 90-degree angles. And then the question, again, just like it was in the last video, the question is, if you're given 2 out of the 3 pieces of information, can you get the third? So the pieces of information are the radii of the circle, the distance between the centers maybe, and the length of the tangent. Maybe that's what you're here to find. On the last one, we had to find the length of the tangent. Let's just say, in this case, we know the radii, and let's say we know the distance between the centers. And so you're stuck with something like this. Let's use this and try to come up with a plan. So let's say we know the radii. Let's get this to be 2. Let's say this is 5. And let's say that we know that the common tangent is 7. Right? So that's a 7. And you can imagine that that creates a very unique situation. A 2, a 5, and a 7. And then the question would be, how long is the distance between D to A? Right? So that's our goal, is to find the distance between the two. Right? Big question mark. And you'll be happy to know that there is a magic rectangle in this situation as well. We want to look at our right triangles, and again, same thing. Label the hypotenuse of the right triangle accurately. So you'll notice, and a lot of students play with this one in the sense that they notice that there's a couple of triangles in here, right? So let's see if I can try to do this. There's a right triangle here, and there's a right triangle here. That's great, and it might be useful later on, but we're going to fall back on this magic rectangle idea and take this line, this AB, which we know to be 5, and I'm going to extend it a little bit. And I'm going to extend it for a length of 2 to match over here. And then I'm going to connect this piece with D. And I'm going to ask you as the viewer, do we know that that is a rectangle? Is that a parallelogram on the inside? And I hope your answer is yes, because we've got a couple of right angles here and here. That makes these lines parallel. We've also made them to be congruent, and we know that if we have a quadrilateral with parallel and congruent opposite sides, that it will be a parallelogram, which is great because what that does is that makes the common internal tangent of 7, it comes over here as well. So this purple line, right, which we said at the beginning was going to be 7. This one is 7. In the given, this will also be 7 over here. There's 7 and 7. What's really nice is that the big thing that we're looking for, the question mark, right, back to our wondering how far apart the centers are, and maybe you've already seen it here now that we have created a whole nother right triangle where we have, oh, this is really interesting. Here's 7. This is a right angle, and there's 7 as well. And so we know that 7 squared plus 7 squared is going to equal question mark squared. And maybe actually you've already figured this out, that this this also is a back to the 45, 45, 90 triangle. If this is 7 and 7, this will have to be, guess? 7 root 2. Now, if you didn't see that and remember that, it would happen over here. This is 49 plus 49 equals question mark squared. Gosh, I got to figure this out. This is 98, which is question mark squared, and that is 49 times 2. So that is 7. Oh, sorry, question mark. Question mark will be root 98, which is 7 root 2. Okay, so magic rectangle, let me just highlight that quickly before we end here. Magic rectangle is, let's see, in pink. Let's make this pink. Magic rectangle falls kind of outside, and that's the rectangle that I'm talking about. Okay, good luck with that one. Common internal tangent line.